Hello everybody, this is the fourth day of our crash course, and we're going to learn LLM training and fine-tuning. Large language models, LLMs, such as GPT, BERT, and T5, represent a major breakthrough in natural language processing, NLP. These models are designed to handle tasks like machine translation, summarization, question answering, and text generation with remarkable accuracy. Built on deep learning architectures, particularly the transformer model, LLMs can understand and generate human-like text by learning from massive datasets. Pre-training, the process of training on vast amounts of general language data, equips the model with the basic understanding of grammar, facts, and word associations. Fine-tuning further adapts the model for specific tasks, improving its performance on specialized applications. This lecture will provide you with a comprehensive understanding of the theory and practical aspects of training and fine-tuning LLMs. By the end, you'll have the necessary knowledge to implement LLMs for various real-world use cases, with a focus on optimization strategies and evaluation metrics. At the core of LLMs are neural networks, which are computational models inspired by the human brain. They consist of layers of neurons, each layer processing input from the previous one. A neuron in a network performs a weighted sum of its inputs, followed by an activation function, which determines the neuron's output. Common activation functions include ReLU, which introduces nonlinearity, and sigmoid, which squashes outputs to a range between 0 and 1. Neural networks use forward propagation to pass input data through layers and compute predictions. Backpropagation is used to adjust the model's weights by calculating the gradient of the loss function and updating the weights accordingly. This process is repeated over many iterations, allowing the model to minimize errors and improve its predictions. Understanding how neural networks work is fundamental to understanding the underlying structure of models like transformers, which form the foundation of modern LLMs. The transformer model revolutionized NLP by introducing an architecture that relies heavily on attention mechanisms, rather than relying on RNNs or LSTM units. It consists of an encoder-decoder structure, where the encoder processes the input data and the decoder generates the output. The attention mechanism, a key component of transformers, allows the model to focus on specific parts of the input sequence when generating output. This self-attention mechanism computes the relationship between words in the sequence, irrespective of their position. This enables transformers to capture long-range dependencies more effectively than RNNs or LSTMs, which struggle with such relationships. Transformers process entire sequences in parallel, leading to faster and more scalable training, and are particularly well-suited for handling large datasets. This architecture has since become the foundation for most state-of-the-art language models, including LLMs, because it overcomes many of the limitations inherent in older models. Pre-training LLMs involves training a model on large and diverse text datasets, such as books, articles, and web data. These datasets enable the model to learn general language features like grammar, sentence structure, and common knowledge. Two common pre-training objectives are masked language modeling, MLM, used by BERT, and causal language modeling, CLM, used by GPT. In MLM, random words in the input are masked, and the model learns to predict them, while in CLM, the model predicts the next word in a sequence. Both objectives teach the model to capture dependencies between words, but the methodologies differ. Pre-training is generally unsupervised, meaning the model learns from raw text without needing explicit labels. The challenge in pre-training lies in handling large amounts of data and ensuring data quality. Training LLMs requires significant computational resources, primarily GPUs or TPUs, which are designed for parallel computation. These devices allow large-scale matrix multiplications, which are central to the operations in deep learning models. In large-scale training, model parallelism is used, where different parts of the model are distributed across multiple devices, enabling faster processing. Additionally, data parallelism is employed, where multiple copies of the model process different parts of the data simultaneously. Cloud platforms such as AWS, Google Cloud, and Azure offer scalable resources, allowing training to be distributed across many machines. However, training LLMs can be extremely expensive, with costs for running a model on GPUs/TPUs for weeks or months reaching millions of dollars. optimization is a critical aspect of training LLMs. The most widely used technique is gradient descent, which iteratively adjusts the model's parameters to minimize the loss function. Stochastic gradient descent, SGD, and ADAM are common variants of gradient descent. ADAM adapts the learning rate for each parameter, which can lead to faster convergence, especially in large models. The learning rate schedule is another important consideration. A common strategy is to start with a larger learning rate and then decay it during training. Some models also employ a warm-up phase, where the learning rate increases before decaying. The batch size, or the number of training samples processed at once, influences both training speed and generalization. A smaller batch size introduces more noise, while a larger batch size may reduce noise but can lead to poorer generalization. Regularization techniques like dropout and weight decay are employed to prevent overfitting. Dropout randomly disables neurons during training, while weight decay penalizes large weights, both of which help the model generalize better. Evaluation of LLMs depends heavily on the specific task at hand. For language models, perplexity is a common metric that measures how well the model predicts the next word in a sequence. Perplexity can be interpreted as the inverse probability of the test set normalized by the number of words, and a lower value indicates better performance. In text generation tasks, such as machine translation or summarization, BLEU and Rouge scores are commonly used. BLEU measures the overlap between the model's output and reference translations, while Rouge evaluates recall and precision in n-gram matching. For classification tasks, accuracy and F1 score are frequently used, where accuracy represents the percentage of correct predictions, and F1 score balances precision and recall. Finally, in more complex tasks, it's important to evaluate how well the model understands the semantics and context of the text. Fine-tuning is the process of adapting a pre-trained model to a specific task or domain. Unlike pre-training, which involves learning general language features, fine-tuning involves further training the model on task-specific data to optimize its performance for that task. This is an example of transfer learning, where knowledge gained from one domain is transferred to a different, often related, task. The primary advantage of fine-tuning is that it allows the model to leverage the vast amount of knowledge learned during pre-training, reducing the need for extensive task-specific, labeled data. Fine-tuning has a wide range of applications, including customer service chatbots, sentiment analysis, legal document classification, and healthcare. To fine-tune an LLM, the first crucial step is preparing a domain-specific dataset. Depending on the task, this could involve specialized data such as medical records, customer service logs, or legal documents. The quality and relevance of the data are paramount, as this is what the model will use to adapt its knowledge. Once you have the dataset, the next decision is whether to freeze some layers of the pre-trained model. Freezing layers helps retain the general knowledge learned during pre-training while focusing the learning on specific task-related features. If the dataset is small, freezing most of the layers and fine-tuning only the last few layers can prevent overfitting. The learning rate for fine-tuning is typically smaller than the pre-training learning rate to avoid drastic changes to the pre-trained weights. Similarly, choosing the appropriate batch size is critical. It must balance training stability and efficiency. Finally, overfitting is a common risk when fine-tuning, especially with limited data. Regularization methods, such as dropout, weight decay, or early stopping, can help mitigate this issue. Monitoring validation performance and making adjustments during training is essential for successful fine-tuning. Transfer learning is a key concept in fine-tuning LLMs. It involves taking a model trained on one task and adapting it to a different, but related task. This approach is highly efficient because it allows models to leverage the knowledge learned from large, general datasets, rather than starting from scratch. In the context of LLMs, this enables them to handle a wide variety of downstream tasks with minimal additional training. Zero-shot learning refers to the ability of an LLM to perform a task without any specific examples or training for that task. The model relies entirely on its pre-trained knowledge and contextual understanding to generate accurate outputs. Few-shot learning, on the other hand, involves providing a small number of examples for the model to learn from. LLMs like GPT-3 excel at zero-shot learning, meaning they can solve tasks such as answering questions or translating text, even if they haven't been explicitly trained on those tasks. Fine-tuning LLMs can be adapted for a wide range of specific tasks. For text classification tasks, such as sentiment analysis or topic categorization, the model is trained to classify input text into predefined categories. For text generation tasks, such as story or article writing, the model is trained to generate coherent and contextually appropriate text. Fine-tuning LLMs for question answering involves adapting the model to understand and extract relevant information from a text to provide precise answers. This can include tasks like reading comprehension or FAQ generation. Sequence labeling tasks, such as named entity recognition (NER) or part of speech (POS) tagging, involve classifying individual words or phrases in a sentence. In NER, the model identifies entities like names, dates, and locations. Fine-tuning for these tasks requires tailoring the model to the particular needs of the application. Hyperparameter tuning is a critical part of training and fine-tuning LLMs. Hyperparameters are settings that affect how the model learns, such as the learning rate, batch size, and number of epochs. The learning rate controls how much the model updates its weights in each step, and a small learning rate can lead to slower convergence, while too large a learning rate might result in instability. Batch size determines how many samples the model processes at once, and epochs define the number of times the model iterates over the entire dataset. Finding the optimal hyperparameter values can be a challenging and time-consuming process. Common methods for hyperparameter tuning include grid search, where all possible combinations of hyperparameters are tested, and random search, which samples random combinations. Bayesian optimization is a more advanced technique, which models the relationship between hyperparameters and model performance to intelligently search for the best settings. While fine-tuning provides significant improvements, there are several challenges to address. Data scarcity is one of the most prominent, particularly when fine-tuning on niche or highly specialized tasks. In such cases, the model might not have enough examples to learn effectively, leading to poor performance. Imbalanced datasets, where some classes are underrepresented, can also negatively affect fine-tuning, as the model may develop a bias towards the overrepresented classes. Another significant issue is overfitting, especially when fine-tuning on small datasets. Regularization techniques and careful monitoring of validation performance are essential to prevent the model from memorizing the training data rather than generalizing from it. The computational cost of fine-tuning can also be substantial, particularly for large models with billions of parameters. Beyond technical challenges, ethical concerns must also be addressed, as LLMs can inherit biases present in the data they are trained on. Fine-tuning LLMs for multilingual tasks presents unique challenges. Language models, particularly those trained on large-scale monolingual corpora, often struggle with multilingual tasks because they lack the linguistic diversity needed for accurate processing. However, multilingual models, such as MBERT, Multilingual BERT, and XLMR, are pre-trained on corpora containing data from multiple languages, allowing them to learn cross-linguistic representations. Transfer learning across languages is possible because these models are exposed to multiple languages during pre-training, allowing them to generalize across different linguistic structures. Fine-tuning a multilingual model on a specific language task involves similar techniques as monolingual fine-tuning, though multilingual models may require more careful tuning due to differences in grammar, syntax, and vocabulary across languages. While multilingual models are highly efficient, their performance on low-resource languages or dialects may be limited, and they often require more computational resources to fine-tune effectively. The field of LLMs is rapidly evolving, with exciting trends shaping the future of AI. One key development is the integration of multimodal learning, where models are trained to process and generate not only text but also images, speech, and other data types. This approach allows models to better understand and interact with the world, leading to more versatile AI systems. Another area of focus is increasing the efficiency of model training and inference. Researchers are exploring techniques like model pruning, quantization, and distillation to reduce the computational cost of LLMs, making them more accessible for practical applications. However, as LLMs become more powerful, ethical concerns become more pressing. Issues such as bias in training data, misinformation generation, and the potential for harmful applications will need to be addressed through regulatory frameworks and improved model design. Model pruning is a technique used to reduce the size of an LLM by removing less important parameters, thereby making the model more efficient without significantly sacrificing performance. There are two main types of pruning: weight pruning and neuron pruning. Weight pruning involves removing individual weights in the model's layers that contribute little to the final output. Neuron pruning, on the other hand, removes entire neurons or layers. By pruning the model, we can achieve a smaller, faster model that is more suited for deployment, especially in resource-constrained environments. While pruning offers clear advantages in terms of efficiency, there are trade-offs. A smaller model may lose some of the fine-grained understanding of language that the larger model had. The key is balancing the size reduction with acceptable performance degradation. Pruning is often combined with other techniques, such as quantization or knowledge distillation, to further enhance efficiency without compromising too much on the accuracy of predictions. Quantization is the process of reducing the precision of model parameters, typically from 32-bit floating point to lower bit representations, such as 16-bit or 8-bit. This reduction can greatly improve the speed and efficiency of inference, making it possible to run models on devices with less computational power, such as mobile phones or edge devices. Quantization helps reduce memory usage and computational cost, which is especially important when deploying large models. However, quantization can introduce challenges, as it may result in a slight degradation in the model's performance due to the loss of precision. The goal is to find a balance where the inference speed is significantly improved without severely compromising accuracy. Techniques such as fine-tuning after quantization can help mitigate the loss of performance, allowing the model to recover from some of the negative impacts of reduced precision. Knowledge distillation is a technique where a smaller model, the student, is trained to replicate the behavior of a larger, more complex model, the teacher. During this process, the student model learns from the teacher's outputs, typically soft targets, rather than hard labels. This allows the student model to approximate the teacher's performance while being more efficient. The advantage of distillation is that it allows us to deploy smaller, faster models that can run in real-time systems, such as chatbots or personal assistants, without needing the massive computational resources of the larger model. Distillation also provides a way to retain much of the knowledge embedded in a large model without incurring the same inference costs. It has been successfully applied in various real-world applications where response time and resource consumption are critical factors. Fine-tuning LLMs with limited data is a critical challenge, particularly for specialized tasks where large annotated datasets are not available. Few-shot learning enables the model to perform a task with only a few examples, which is ideal when labeled data is scarce. To fine-tune with limited data, techniques like data augmentation and synthetic data generation can help. Data augmentation involves creating variations of existing data, such as paraphrasing sentences, to artificially expand the dataset. Synthetic data can also be generated by leveraging other models or simulating data to resemble real-world examples. Additionally, strategies such as transfer learning, where a model pre-trained on a large corpus is adapted to a small task-specific dataset, can enhance performance. Regularization methods like early stopping, dropout, or data noise addition help mitigate the risk of overfitting to small datasets. Ethical considerations are crucial when training LLMs, as the models may inherit and amplify biases present in the data they are trained on. Bias in training data, whether it's racial, gender, or ideological bias, can lead to unfair, discriminatory, or harmful outputs. Identifying and mitigating bias requires careful data curation, continuous monitoring, and the use of debiasing techniques such as adversarial training or bias correction algorithms. Ensuring fairness and inclusivity is vital, especially for models deployed in sensitive domains like hiring, healthcare, and criminal justice. Ethical guidelines, such as those proposed by organizations like OpenAI and the IEEE, emphasize the need for transparency, accountability, and the consideration of societal impact when developing and deploying LLMs. By adhering to ethical principles and conducting thorough evaluations, we can build more trustworthy AI systems. One of the significant risks of LLMs is their potential to generate false or misleading information. Given the vast amount of unverified data on the internet, LLMs can sometimes produce factually incorrect outputs based on patterns in their training data. Detecting and filtering out harmful content is a growing area of research. Fact-checking systems, which verify the information generated by the model against reliable sources, are being integrated into many systems to mitigate misinformation. Moreover, developing LLMs that are accountable and transparent about the sources of their information can help users understand the context and reliability of the generated content. Approaches like provenance tracking, where the model's reasoning process is made transparent, can help address concerns about misinformation. GPT-3, developed by OpenAI, is one of the most advanced LLMs available today. With 175 billion parameters, it has demonstrated remarkable abilities in text generation, translation, summarization, and more. GPT-3's flexibility allows it to be fine-tuned for specific tasks such as content creation, customer service, and programming assistance. In content creation, GPT-3 can generate coherent and contextually appropriate articles, blogs, and stories. Fine-tuning GPT-3 for specific tasks can involve adjusting the model with task-specific datasets, allowing it to perform even better for a particular domain. However, using GPT-3 also presents challenges, such as ensuring that it doesn't generate inappropriate content or reinforcing biases. The lessons learned from deploying GPT-3 emphasize the need for careful monitoring, ethical considerations, and continuous model updates to ensure reliable and fair performance. The future of LLMs looks promising, with several exciting areas of research that aim to improve the scalability, efficiency, and capabilities of these models. One area of focus is scaling up models while making them more efficient. This includes exploring techniques like sparsity, pruning, and better hardware optimizations to reduce computational requirements. Cross-modal AI systems, which combine text, images, and video, are also on the horizon. These systems would allow AI to better understand the world by processing multiple forms of input simultaneously, leading to more advanced capabilities like visual question answering and autonomous driving. Interpretability and explainability remain critical issues in LLM research, as understanding how models make decisions will be essential for trust and accountability. Finally, researchers are also looking at ways to use LLMs to address pressing social issues, such as combating misinformation, enhancing accessibility, and improving education. As these models continue to evolve, their impact on society will be profound, making it essential to approach their development thoughtfully. Fine-tuning LLMs for specialized domains, such as legal, medical, or technical fields, provides significant advantages by tailoring models to specific vocabularies and contextual knowledge. In legal fields, for example, models need to understand complex legal terminology, while medical models must be trained on healthcare-specific language, like diseases, treatments, and medications. Domain adaptation techniques, such as transfer learning and fine-tuning on domain-specific datasets, are essential to customizing LLMs for these tasks. Handling domain-specific vocabulary requires careful curation of training data and may involve creating custom tokens for highly specialized terms. During fine-tuning, the model must maintain generalization while also achieving accuracy in these domains. To ensure relevance and accuracy, it is critical to continuously validate the model against real-world use cases. Hyperparameter tuning is essential to optimizing the performance of LLMs during fine-tuning. One of the first considerations is selecting the right optimizer. Optimizers like Atom or its variants are widely used for LLMs, as they offer adaptive learning rates that are beneficial when fine-tuning on smaller datasets. Another best practice is dynamically adjusting the learning rate during training. A learning rate schedule, such as learning rate annealing or the warm-up strategy, can help the model converge more effectively while avoiding overshooting during the early training phases. The batch size also plays a key role, with smaller batch sizes helping improve generalization but requiring more frequent updates. Early stopping is another effective strategy to prevent overfitting, where the training process is halted when the validation performance stops improving. Cross-validation, where the model is trained on different subsets of the data, helps assess its generalizability and robustness across various data points. LLMs often struggle with tasks that require understanding long-range dependencies in text, such as long-form document analysis or dialogue systems. The transformer architecture, with its self-attention mechanism, mitigates some of these challenges by allowing the model to focus on relevant parts of the input regardless of distance. However, as input sequences grow longer, transformers can become computationally expensive and less effective in capturing distant relationships. To address this, various techniques have been proposed, including memory augmentation and recurrent architectures that help the model retain long-term context across input sequences. Another approach is the use of sparse attention mechanisms, which focus attention on key parts of the text rather than the entire input. These methods allow the model to capture long-range dependencies more effectively, making it more suitable for tasks like summarization, document retrieval, or extended conversations. To enhance the performance of LLMs on specialized tasks, incorporating external knowledge sources is increasingly important. One approach is knowledge retrieval, where the model fetches relevant information from external databases or the web to support its predictions. For instance, an LLM used for legal or medical queries might access databases containing case law or clinical guidelines. Another technique is integrating structured data, such as knowledge graphs or tables, which allow the model to interact with factual, organized information more effectively. Hybrid models that combine an LLM with external knowledge sources can offer significant benefits. By relying on both learned representations from large corpora and specific, structured external information, these models can provide more accurate, context-aware outputs. This is particularly useful for applications in fields like finance, where real-time data is critical for decision-making, or in healthcare, where evidence-based information is essential. Efficient inference is crucial when deploying LLMs in production, particularly in applications that require real-time responses, such as chatbots, virtual assistants, and search engines. One of the key techniques for improving inference speed is quantization, where the model parameters are reduced to lower bit precision. This can drastically speed up the model and reduce memory usage, making it more suitable for edge devices. Pruning also helps by removing unnecessary weights or neurons, reducing the model size. Another strategy is model distillation, where a smaller student model is trained to mimic the outputs of a larger teacher model, preserving much of the knowledge while improving efficiency. Deployment on specialized hardware, like TPUs or GPUs, can also improve inference speed significantly, especially when handling large-scale models. Optimizing these factors ensures that LLMs can operate efficiently and at scale, while maintaining response time and performance. Adversarial attacks in NLP involve input modifications designed to deceive a model into making incorrect predictions. These attacks can be subtle, such as replacing a few words in a sentence or reordering text, yet they can cause significant errors in the model's outputs. Common methods for generating adversarial examples include gradient-based attacks, where small perturbations are made to the input data based on the model's gradients, and text-based attacks, such as synonym substitution. To improve robustness, LLMs can be fine-tuned on adversarial examples to help them learn to identify and reject deceptive inputs. Regularization techniques, like adversarial training, where the model is exposed to both clean and adversarial examples during training, can also help. Evaluating model robustness through adversarial testing ensures that the model can maintain accurate predictions even under manipulation. As LLMs become more integral to AI systems, ensuring their responsible use is vital. Transparency is one of the core principles, ensuring that the decision-making process of LLMs is understandable to users and developers alike. This can involve providing explanations for model outputs or ensuring that the model's behavior is interpretable. Data privacy and security are also essential concerns, especially when LLMs are trained on sensitive or personal data. Ensuring compliance with data protection laws, such as GDPR, and employing privacy-preserving techniques, like differential privacy, can help mitigate risks. Accountability for AI-generated content is another critical issue. If an LLM produces harmful or incorrect outputs, it's essential to have mechanisms in place for addressing these mistakes. Finally, developing guidelines for responsible deployment is crucial. These should outline best practices for using LLMs in a way that promotes fairness, reduces bias, and minimizes negative societal impacts. Interpretability in LLMs is crucial for understanding how models arrive at their predictions, ensuring trustworthiness, and identifying potential biases or errors. One of the key techniques for interpretability is attention visualization, which helps visualize how different words or tokens in the input sequence influence the output. By examining attention weights, we can gain insight into what parts of the text the model is focusing on when generating predictions. Probing techniques are also useful, as they involve training simple classifiers on intermediate layers of the model to understand how the model processes different linguistic features. Another advanced technique is layer-wise relevance propagation, LRP, which assigns relevance scores to the model's layers based on their contribution to the final prediction. LRP can help visualize which parts of the input most influenced the model's decision. Tools like SHAP, Shapley Additive Explanations, and LIME, Local Interpretable Model Agnostic Explanations, can further facilitate interpretability by offering insights into model decisions in a more user-friendly manner. Transfer learning is a powerful approach for training large models like LLMs, where a model is first pre-trained on a large, generic corpus before being fine-tuned on task-specific data. Pre-training allows the model to learn general language patterns, relationships, and structures across a wide range of domains. Once pre-trained, the model can be fine-tuned on more focused datasets to adapt it for specific tasks such as sentiment analysis, machine translation, or named entity recognition. The primary benefit of transfer learning is that it allows the model to leverage knowledge learned from vast amounts of data, improving performance on smaller, task-specific datasets. However, one of the challenges is ensuring that the pre-trained model's knowledge is relevant to the specific task at hand. Fine-tuning also requires careful attention to avoid overfitting to the task-specific data, especially when the dataset is small. LLMs can inherit and even amplify biases present in the training data, which can lead to unfair or discriminatory behavior. These biases can stem from biased data sources, such as social media or historical texts, or from the design of the algorithms themselves. Identifying and measuring fairness in LLMs involves the use of fairness metrics, which assess whether the model's predictions are biased against certain groups or demographics. Examples of fairness metrics in NLP include demographic parity, equalized odds, and calibration by group. Debiasing techniques, such as adversarial debiasing or bias correction algorithms, aim to minimize these biases during the training process. In some cases, training data itself can be adjusted by oversampling underrepresented groups or using bias correction methods. The impact of biased models can be profound, especially in sensitive domains like hiring, healthcare, and law enforcement, where biased predictions can lead to unfair outcomes. Data augmentation is an essential technique when fine-tuning LLMs, especially when working with limited labeled data. In NLP, data augmentation involves creating new training examples by applying transformations to the existing dataset. Some common techniques include paraphrasing, backtranslation, and synonym replacement. Paraphrasing involves rewording sentences to create variations of the original text, while backtranslation generates new text by translating the original text into another language and then back to the original language. This process introduces new syntactic and lexical variations. Synonym replacement swaps words with their synonyms to diversify the vocabulary without changing the meaning of the text. While data augmentation helps improve model generalization, there are challenges in ensuring the augmented data maintains high quality and relevance to the task at hand. Zero-shot learning refers to the ability of a model to perform a task without having been explicitly trained on task-specific data. In the context of LLMs, zero-shot learning is possible due to the vast amount of general knowledge the model acquires during pre-training on large text corpora. LLMs like GPT-3 have demonstrated remarkable zero-shot capabilities, allowing them to handle tasks such as text classification, question answering, and summarization without specific fine-tuning. This is achieved by leveraging the model's general understanding of language and its ability to generalize across tasks. Zero-shot learning has many applications, particularly in scenarios where labeled data is scarce or unavailable. However, there are limitations and challenges, including the model's tendency to struggle with tasks that are very different from those seen during pre-training, or tasks that require specialized knowledge. Zero-shot learning also depends heavily on the quality and diversity of the data the model was exposed to during training. Distributed training is a crucial technique for scaling LLMs, especially when dealing with massive models that cannot fit into the memory of a single machine. There are two primary strategies for distributed training: data parallelism and model parallelism. In data parallelism, the dataset is divided across multiple machines, and each machine computes gradients based on a subset of the data. The gradients are then aggregated to update the model parameters. In model parallelism, the model is split across multiple machines, each handling a portion of the model's parameters. This is particularly useful when the model is too large to fit into the memory of a single device. While distributed training enables the training of large models, it also presents challenges, such as synchronization overhead, communication bottlenecks, and ensuring consistency across devices. Tools like Horovod, DeepSpeed, and PyTorch's distributed data parallel offer frameworks to handle these challenges efficiently and scale up training for large models. Building a robust and scalable LLM deployment pipeline involves several key components. First, data pre-processing and tokenization are crucial steps for preparing raw text data for training. Tokenization breaks down text into smaller units, such as words or subwords, that the model can process. The model training and fine-tuning stages follow, where the model is trained on large datasets and then fine-tuned for specific tasks or domains. During this phase, hyperparameter optimization and regularization techniques are employed to achieve optimal performance. After deployment, it's critical to monitor the model's performance in real time, ensuring that it continues to provide accurate and relevant outputs. Post-deployment monitoring includes tracking model drift, where the model's performance may degrade over time as the input data distribution changes. Regular updates and retraining may be necessary to maintain high-quality performance, especially in rapidly evolving fields or dynamic environments. Modern LLMs are capable of handling multilingual tasks by training on large datasets that include multiple languages. These models can understand and generate text in several languages, often without the need for separate models per language. The training process involves exposing the model to diverse linguistic data, enabling it to learn commonalities across languages. Cross-lingual learning allows a model to transfer knowledge between languages, meaning it can perform tasks in a language it has seen less data for, by leveraging knowledge from languages with more data. However, fine-tuning multilingual models presents challenges, such as balancing the representation of all languages and managing issues like domain-specific vocabulary across languages. Ensuring that the model handles each language effectively while maintaining strong generalization requires careful tuning and potentially domain adaptation. Continual learning involves training models incrementally, so they can adapt to new data or tasks without forgetting previously learned information. One major challenge in continual learning for LLMs is catastrophic forgetting, where the model forgets old knowledge as new knowledge is introduced. Techniques like elastic weight consolidation help mitigate this by preserving the importance of existing weights while adapting to new data. Memory-augmented networks also allow the model to store and recall information from previous tasks. Continual learning is valuable for applications where models need to adapt to rapidly changing information, such as news aggregators or dynamic customer support systems. It enables models to stay up to date without retraining from scratch, which is both time and resource efficient. Training LLMs in low-resource settings, where data is scarce, is a significant challenge. One approach is to pre-train models on multilingual or general corpora, which increases the breadth of knowledge the model can access. Data-efficient techniques such as few-shot learning and transfer learning help mitigate this issue. Few-shot learning allows models to perform tasks with minimal examples, while transfer learning leverages pre-trained knowledge to adapt models to specific tasks even when little task-specific data is available. Despite these approaches, limited data can still affect model performance, especially for niche applications where data may be sparse. Balancing model size, computational resources, and data availability is key in achieving reasonable performance in low-resource scenarios. Low-rank adaptation, LoRA, is an efficient technique for fine-tuning large language models, LLMs, with fewer parameter updates. Traditional fine-tuning often requires updating a vast number of parameters, which is computationally expensive and memory-intensive. LoRA addresses this by freezing the original model weights and adding low-rank trainable matrices to adapt the model to new tasks. This reduces the number of parameters that need to be updated, improving efficiency without compromising performance. LoRA is particularly beneficial in resource-constrained environments where computational power and memory are limited. In large-scale applications, LoRA helps streamline the fine-tuning process while maintaining high model performance. By using LoRA, organizations can deploy large models for specialized tasks without requiring extensive computational resources, making it a popular technique for practical applications. Prompt engineering is the practice of designing input prompts to guide language models toward generating the most accurate or relevant responses. The success of many LLM-based applications heavily depends on the quality of the prompt, as small changes in wording can drastically affect the output. Effective prompt construction involves providing sufficient context, being specific in what is being asked, and ensuring that the prompt aligns with the task or domain. Best practices include using clear instructions, avoiding ambiguity, and leveraging examples where necessary. The quality of prompt engineering significantly impacts model performance, as it enables the model to better understand the user's intent and produce more coherent and accurate responses. Over time, prompt engineering has become a crucial skill in maximizing the potential of LLMs in various applications, from chatbots to data analysis. Zero-shot learning refers to a model's ability to perform tasks without having seen specific examples during training. In the case of zero-shot text classification, LLMs leverage their general understanding of language to classify text into predefined categories even without task-specific labels. This is especially useful when labeled data is scarce or unavailable. With pre-training on vast corpora, LLMs acquire broad general knowledge that can be applied to new, unseen tasks. The benefit of zero-shot classification lies in its versatility. It allows LLMs to be used in a wide range of applications without needing extensive retraining. However, the approach has its limitations, including potential inaccuracies in highly specialized tasks or areas where the model's training data is insufficient. Despite these challenges, zero-shot text classification has become an essential tool for quickly deploying LLMs to new domains. Fine-tuning LLMs on domain-specific data is crucial for improving their performance in specialized fields, such as law, medicine, or finance. General-purpose LLMs may struggle with domain-specific terminology or nuanced language, which is why fine-tuning on task-specific or domain-specific corpora helps models perform more accurately in those contexts. Strategies for adapting models to specific fields involve using labeled datasets from the target domain and adjusting hyperparameters to maximize task-specific performance. The primary benefit of domain-specific fine-tuning is the incorporation of specialized knowledge, enabling more accurate and contextually relevant results. However, there are pitfalls to consider, such as overfitting to the domain data, limiting the model's generalization ability, and ensuring that the model can handle edge cases appropriately. Careful validation is essential to ensure that domain adaptation does not result in unintended biases or errors. Model distillation is a technique that involves transferring the knowledge from a large, complex model, the teacher, to a smaller, more efficient model, the student. The goal of distillation is to create a model that can achieve similar performance to the larger one while requiring fewer resources in terms of memory, computational power, and storage. This process is particularly important when deploying models to environments with limited computational capacity, such as mobile devices or edge computing. Distilling large LLMs into smaller versions allows for efficient real-time inference while maintaining acceptable performance. However, there are trade-offs to consider. Distilled models may lose some accuracy compared to the original large models, so it is important to find the right balance between model size and performance. Despite these trade-offs, model distillation remains a key technique for deploying LLMs in production environments. Multitask learning is a training approach where a model is simultaneously trained on multiple tasks, allowing it to learn shared representations that benefit all tasks. In the case of LLMs, this could involve training a model to handle several NLP tasks, such as sentiment analysis, question answering, and text classification, using the same model architecture. The benefit of multitask learning is that it enables the model to generalize better by learning shared patterns across tasks, which can improve performance on each individual task. Additionally, this approach is more resource efficient, as it reduces the need for separate models for each task. However, challenges include ensuring that the model does not underperform on any individual task due to conflicting gradients or task-specific requirements. With careful tuning and task balancing, multitask learning can significantly enhance LLM performance and versatility. Knowledge graphs are structures that represent relationships between entities in a graph format, typically consisting of nodes, entities, and edges, relationships. LLMs can play a pivotal role in both constructing and querying knowledge graphs. By understanding context and relationships between words, LLMs can extract entities and their relationships from text, aiding in the construction of knowledge graphs. Additionally, LLMs can be used to query knowledge graphs, interpreting user input and identifying relevant information from the graph. The integration of LLMs with knowledge graphs provides several benefits, including improved information retrieval, better decision-making, and enhanced data understanding. In sectors like healthcare and finance, this integration enables more accurate predictions, insights, and recommendations by leveraging both structured and unstructured data. Model compression is a strategy for reducing the size of large language models to improve their deployment efficiency, particularly in environments with limited computational resources. Techniques like pruning, removing unnecessary weights, quantization, reducing the precision of model parameters, and matrix factorization are commonly used to compress LLMs without significantly sacrificing performance. The goal is to create a smaller model that can still make accurate predictions but requires less memory and processing power. Compressed models are particularly valuable for deploying LLMs in edge devices, such as smartphones or IoT devices, where computational resources are limited. Although compression can result in a slight drop in accuracy, the trade-off between performance and efficiency can often be justified in practical use cases, especially when real-time processing is required. Reinforcement learning, RL, in NLP involves training models through interaction with an environment to optimize a reward function. When applied to LLMs, RL can be used to fine-tune a model based on feedback from specific tasks or user interactions. For example, an LLM can be trained to generate responses that maximize user satisfaction or engagement, with the reward signal coming from user feedback or preset evaluation criteria. The main benefit of RL fine-tuning is its ability to adapt models to dynamic environments where traditional supervised learning might be less effective. However, RL fine-tuning poses challenges, including the difficulty of defining appropriate reward functions and ensuring stable training. Furthermore, RL for LLMs can be computationally expensive, especially when the interaction environment is large or complex. Synthetic data refers to data that is artificially generated rather than collected from real-world sources. In NLP, synthetic data can be used to fine-tune LLMs by generating text samples that resemble real-world data. This is particularly useful in scenarios where obtaining labeled data is expensive or time-consuming, or when training data for specific tasks is scarce. Synthetic data generation methods include rule-based approaches, data augmentation, or leveraging pre-trained models to generate plausible examples. The primary benefit of synthetic data is the ability to rapidly scale the training process, filling gaps in data coverage and improving model performance on niche tasks. However, using synthetic data also comes with challenges, such as ensuring the generated data is diverse and representative of real-world scenarios. Additionally, the model may overfit to patterns present in synthetic data, which may not perfectly align with real-world data distribution. Hyperparameters in LLMs are the parameters that govern the model's training process, such as the learning rate, batch size, and the number of layers. Tuning these hyperparameters is crucial for optimizing model performance and ensuring efficient training. Hyperparameter tuning involves selecting the optimal combination of parameters to achieve the best model accuracy while minimizing overfitting or underfitting. Common techniques for hyperparameter search include grid search, where all possible combinations are tested, and random search, where hyperparameters are randomly sampled. More advanced techniques such as Bayesian optimization or reinforcement learning can also be employed to optimize hyperparameters efficiently. Best practices for hyperparameter tuning include using a validation set to monitor model performance, considering the computational cost of searching large hyperparameter spaces, and applying early stopping to avoid overfitting during training. Overfitting occurs when a model learns to perform exceptionally well on training data but struggles to generalize to new, unseen data. In the context of LLMs, overfitting can manifest as memorization of specific patterns or noise in the training data, leading to poor performance on real-world tasks. Detecting overfitting typically involves monitoring the model's performance on a validation set during training and looking for discrepancies between training and validation metrics. Methods for reducing overfitting include regularization techniques such as L2 regularization, which penalizes large weights, and dropout, where randomly selected units are dropped during training to prevent reliance on specific neurons. Overfitting negatively impacts the model's ability to generalize, making it less effective for deployment in real-world applications. Effective regularization and training strategies help mitigate this issue, ensuring that models can perform well across a variety of tasks and datasets. Transfer learning involves leveraging a pre-trained model on one task and adapting it to a new, but related, task. In LLMs, this means using a model that has been pre-trained on a large corpus of data, then fine-tuning it on a smaller, task-specific dataset. The pre-trained model has already learned a wide range of language patterns and general knowledge, which it can apply to the new task, making transfer learning highly effective for tasks with limited labeled data. Benefits of transfer learning include faster training, improved performance with smaller datasets, and reduced computational costs. However, transfer learning also has challenges, such as ensuring that the model adapts appropriately to the new task without forgetting its pre-existing knowledge, catastrophic forgetting, or overfitting to the new dataset. Despite these challenges, transfer learning remains a foundational approach for modern NLP tasks. Zero-shot learning in NLP refers to the ability of a model to perform a task without having been explicitly trained on examples of that task. For LLMs, zero-shot classification enables them to categorize text or perform other NLP tasks based solely on the instructions given, without needing task-specific labeled data. Zero-shot models can generalize across different tasks by leveraging the broad knowledge acquired during pre-training. The advantage of zero-shot learning is that it reduces the need for task-specific fine-tuning, allowing models to adapt to a wide range of problems with minimal data. This is particularly useful in applications where new tasks emerge regularly, such as chatbots, or when training data is not available. However, zero-shot models may struggle with highly specialized tasks or uncommon topics, where more explicit training would be necessary to achieve high performance. Cross-domain adaptation involves transferring a model's knowledge from one domain to another, often with minimal domain-specific data. In LLMs, this means using a model trained on general language data and fine-tuning it to perform well in a specific domain, such as healthcare, finance, or law. Techniques for cross-domain adaptation include domain-specific pre-training, where a model is exposed to a limited amount of domain-specific data, or the use of adapters, lightweight layers that allow a pre-trained model to specialize in a particular domain. Challenges in cross-domain fine-tuning include ensuring that the model doesn't overfit to the small amount of domain-specific data while still adapting to the nuances of the new domain. Use cases for cross-domain adaptation are widespread in industries where models need to understand specialized terminology and context, such as medical diagnostics or legal document analysis. Multimodal fine-tuning refers to the process of training a model to handle data from multiple modalities, such as text, images, and audio. For LLMs, this means adapting the model to work with a combination of text data and other types of input, enabling more comprehensive understanding and generation capabilities. Training LLMs on multimodal data allows them to handle tasks like image captioning, video summarization, or answering questions based on images and text. Applications for multimodal models span a variety of industries, from robotics, where models can understand both visual input and natural language instructions, to healthcare, where models may need to process medical images alongside textual records. However, challenges in multimodal fine-tuning include the need for large, diverse datasets that cover all modalities effectively, as well as the technical difficulties in aligning different types of data so the model can process them cohesively. Active learning is a semi-supervised learning technique where the model actively selects the most informative examples to be labeled by humans. This allows for more efficient fine-tuning by focusing on the data points that are most uncertain or representative of the task, minimizing the amount of labeled data required. In the context of LLMs, active learning can be used to iteratively refine the model by selecting challenging examples that will most likely improve its performance. The primary benefit of active learning is its ability to reduce the need for large amounts of labeled data, making it especially useful in resource-constrained environments where labeling data is expensive or time-consuming. Techniques for implementing active learning include uncertainty sampling, selecting examples where the model is most unsure, and query by committee, selecting examples where multiple models disagree. While effective, active learning does require careful management to ensure that the selected examples are truly representative and diverse. Knowledge distillation is a process where a smaller model, the student, is trained to emulate the behavior of a larger, more complex model, the teacher. In LLMs, this technique is used to transfer the general knowledge learned by a large, pre-trained model to a smaller, more specialized model, making it more efficient for specific tasks. The advantage of knowledge distillation lies in its ability to create lighter, faster models with fewer parameters, which are crucial for deployment on devices with limited computational resources, such as mobile phones or IoT devices. While smaller models benefit from the knowledge transfer, there is a trade-off in terms of performance. The distilled model may not fully match the accuracy or capabilities of the larger teacher model. However, with careful fine-tuning and optimization, knowledge distillation allows for an effective balance between computational efficiency and model performance. Pre-trained LLMs have revolutionized the field of NLP by enabling transfer learning on a broad scale. Transfer learning involves using a pre-trained model as the starting point and fine-tuning it on task-specific data to optimize performance. These pre-trained models are trained on massive datasets and have learned general language patterns, making them powerful foundations for a variety of NLP tasks, such as text classification, sentiment analysis, and machine translation. The benefits of using pre-trained models for fine-tuning include reduced training time, improved performance, and the ability to handle tasks with limited labeled data. Adapting pre-trained models to specific tasks is done through further fine-tuning on domain-specific data. However, challenges can arise in the form of catastrophic forgetting, where the model's general knowledge is lost as it focuses on the new task. Fine-tuning strategies such as careful regularization and task-specific training data can mitigate this risk. As LLMs continue to evolve, the future of fine-tuning presents exciting opportunities and challenges. Emerging techniques such as few-shot learning, multimodal fine-tuning, and unsupervised learning are paving the way for more efficient and flexible model adaptation. Future research is likely to focus on improving the efficiency of fine-tuning, especially in resource-constrained environments, as well as addressing ethical concerns related to model biases, data privacy, and fairness. Ethical considerations will play an increasingly important role as LLMs become more integrated into decision-making processes across various industries. Additionally, as LLMs grow in size and complexity, the challenges associated with their fine-tuning and deployment will require innovative solutions. The integration of LLMs into diverse domains, from healthcare to education to autonomous systems, presents tremendous opportunities, but also demands careful attention to ensure that models are developed, deployed, and maintained responsibly. Thanks for watching. For more technical courses and interview materials, please go to bowsy8.com.